Can you all hear me? Hello everyone, sorry for the delay. Let me know in the live chat if you can hear me. I'll be looking at it. Hi Sumit. Yeah, I will be, it's just that there's been I will be taking math lectures more often. It's usually going to be thrice a week or more. Do let me know if you can hear me. I'm here right now. I just moved cities, so there's going to be a bit of delay. The frequency was lesser. I'm sorry about that. Let me know in the live chat if you can hear me. Let's try out a few things. Sumit, can you tell me if you can hear me in the live chat? Audible. Thanks, Kage. Just replace. Okay. All right. Good morning, everyone. Hope you're all doing well. So hi everyone. My name is Sai Avinash. Sinus070 is my nickname. I'm currently working as an SRE at Google Dublin. My All India rank in CodeChef is 3. I'm a 7-star coder. I'm maxed at International Master at CF. I'm currently a master right now. I previously interned at Uber and I'm a Snackdown finalist. So the subjects that I take are discrete maths, dynamic programming, graphs, and a lot of other competitive programming topics. Use the code SciLife to get a 10% off on the Unacademy Plus subscription. So what do you get with the Plus subscription? What are the benefits? You get to interact with India's best programmers live. You get complete doubt support. And you get to practice problems, and if you have any doubts with them, you can get them clarified with India's best programmers. Use the code SciLife to get a 10% off on the Unacademy Plus subscription. So let me know if if everything's audible and everything's good from my end. I shall. If everything's okay, I can proceed to the next part. So this is a career as a developer subscription. It's $9.99 per year, and it's about getting placed at as you can see, enthusiasts in the software and technology domain who want to enable lifelong learning. It's for them. So there's a college projects show every night at 10 p.m. It starts from 6th August, which is today. It's taken by Raj, Striver. He's an SD at MediaNet and a 6-star code chef. So he'll be taking the college projects here at every Friday night, 10 p.m. Do check it out. So if you think this content is going to be useful to you, I think it's going to be if you're really starting as a programmer, if you're just starting college, or even if you're midway, this content is going to be useful for you. Do like, share, and subscribe. So today, are we taking the course? Are we taking the topic math programming? So, what is this? Like modular arithmetic. So modular arithmetic, it's basically dealing with reminders of numbers with respect to another number instead of the actual number itself. Okay, what does that mean? Reminders of numbers means when you have two numbers 10 and 7, 10 gives the reminder 7 modulo 10 gives the reminder 3 modulo 7, correct? Now what does the number 45 give modulo 7? it gives the remainder 3. Exactly. So what does it mean? I should just clear this. How do I clear this? Okay, wait, I don't need all this. Sumit, what's SRE versus SWE? Well, they deal with different things. Like I I shall let you know in a different video or something. But let's not digress from this topic. Sorry about that. Okay. Yeah. Now I use a pencil here. All right. Awesome. So, um, what is modular arithmetic like? It's just taking mod basically. It's the math revolving around. Hi Harini, we're doing well. So it's the math revolving around taking mod, like wrapping around numbers, like So what's it useful for? Like you have a clock, 1, oh, so it's 12, 1, this is 6, this is 9, so on. So say you start at 12, and at each step, I'll just draw these things. Apologies for my handwriting. Yeah. So after you start at say 12, you start over here 12. Now where will you be after 35 rounds? Where will you be after 35 rounds? So to answer questions like this is where modular arithmetic comes in. So you go one by one round 12, another round 24, another round 36, but you need 35, so you go one back, which is just 11. So 35 gives the remainder 11 modulo 12. I mean, this is something which is like basic knowledge. So how do you calculate modulo? So you, like 35 modulo 12. How do you calculate this? It's basically you keep removing 12 from 35 until you can't remove it anymore. It's as simple as that. It can be 0 as well. So 36, you remove 12 once, you get 24. You remove 12 again, you get 12. You remove 12 again, you get 0. So 0 is the remainder of 36 modulo 12. Fairly straightforward. All right. So modulo is basically wrapping around and ignoring the wraps, basically ignoring the wraps, and whatever is left over is the modulo. All right. All right. Trick question. I mean, it's basically you need to add or subtract a multiple. Adding is for negative numbers. That's a bit trickier, but it's okay. That's okay. So for example, minus 7 modulo 3. Minus 7 modulo 3. Who can tell me what's minus 7 modulo 3? Someone comment on the chat, please. Here the definition is slightly different. How many times can you add a number till it's just above 0, greater than or equal to 0? Who can tell me the answer to this question? Minus 7 modulo 3. Yep. The answer to minus 7 modulo 3 is simply 2 because how do I, okay, this is something new to me. One sec, I just need to clear the board. Let me just search clear. Yep, I'll just clear this. Awesome. So, yep, Divakaran has the right answer. Minus 7 modulo 3 is 2. Why? Because minus minus 7 modulo 3 is 2. Because minus 7, you add a 3, it gives you minus 4. You add a 3, you get minus 1, not yet above 0. And you add another 3, you get 2. So that's why, that's what's the modulo. So it's, you take or add a multiple to get as close to 0 as possible while being above 0. That's the definition of modulo. Awesome. So what different do you do in your code? Like in a lot of problems, they ask you, they give you a combinatorics problem and then they ask you to compute the answer modulo prime. Why do they ask you first of all? Why? Because your computer has limited storage, right? Now, say the answer is of the form 3 to the power 1000 or like 3 to the power 1000 or 100 choose 50. It's 100 factorial. It involves computing factorials. It's not so easy to put that out in code. Like each integer is simply, it's just a 32-bit, like it's stored as a 32-bit or a 64-bit number in your computer, correct? 32-bit is like up to 10 power 9, 64-bit is up to 10 power 18, 4 into 10 power 18 or something. But like, it does not, what do you say? Like it does not cover numbers like 100 factorial or 2 to the power 1000. 2 to the power 1000 is a lot, like it's, I don't know, it's about 10 to the power 300. But you can calculate only up to 10 to the power 18. So you need to shorten the number somehow. So that's the reason they ask you to compute modulo a big prime, modulo 10 to the power 9. Note that if you take modulo a number p, like modulo number 7, the number is always going to be, the remainder is always going to be from 0 to p minus 1. Because if it's above p, you just remove p and then it leaves from 0 to p minus 1. Like you keep removing p till you get from the number till you get from 0 to p minus 1. That's what it means, right? So in a lot of problems, they ask you to calculate. The answer modulo p. Like for example, the question can be as simple as there are given n, what is the number of possible coin causes, and n is up to 3000 or n is up to 10 power 5. Now you can just do 2 to the power 10 to the power 5 and print the answer, like multiply 2 one by one. But in a lot of programs like C++ or Java, the integer is up to 10 to the power 18 itself. 10 to the power 18. That's it. It can't support 10 to the power 2 to the power 10 power 5, which is a huge number. That's why they ask you to take modulo p. Well, if you print now you might ask, if you print the answer modulo p, like 2 to the power 10 power 5 modulo p, it's going to be between 0 to p minus 1. Like p, say, they might ask you to print 2 to the power 10 to the power 5 modulo p, where p is about 10 to the power 9 plus 7. Modulo prime, they usually ask you to print modulo prime. I'll tell you why later. Like there's a reason behind that. Now you might ask like, say 2 to the power 10 to the power 9 plus 7 is say 46 or something you get, for example. Let's say 46. Now you might think like different powers of 2 can map to 46 as well. Like how do they know that you've computed it correctly? Yep, they're taking a chance. Like If modulo p 2 to the power 10 power 5 modulo p matches, they think that you've computed it correctly. You computed the answer correctly. That's why they ask you to print only 2 to the power 10 power 5 modulo p. Alright. Awesome. Now what different do you do in your code? We'll just take a small example. Let's compute 2 to the power 10 power 5 modulo p itself. Let's take the example of binary exponentiation. So what we do here differently is, every time we do multiplication or addition, we take mod, because if we don't take mod, it might overflow the limit of 10 to the power 18. Alright, I'll just do an example here. I hope everything's clear so far. Like, if there's any doubt, do ask me in the live chat. I'm staring at it. We use long because integer is just up to 10 power 9 and mod is say const ll mod. Note that I'm using a type def here, which means I don't have to type long every time. I can get away with just typing ll mod equals 1 2 3. Note that this number is a prime, like it's a commonly used modulo, and if you have tried solving problems on different sites, you might notice that this is a commonly used modulo. One reason is it's a prime, and another reason is close to 10 power 9, because why do we need 10 power 9? It's because our integers are up to 10 power 9 and longs are up to 10 to power 18. And in a lot of combinatorial problems, it involves multiplying two numbers. And we know that multiplying two numbers. Oh wait, I forgot to tell you this, right? So, modular arithmetic, it follows this property: a into b modulo p is a modulo p into b modulo p modulo p. So you can take the number 5 and 7 and modulo 3. 5 modulo 3 into 7 modulo 3. What's 5 modulo 3 into 7 modulo 3? 5 modulo 3 is 2, 7 modulo 3 is 2, 2 into 2 is 4, and again 4 modulo 3, it's 1. 5 into 7 modulo 3, sorry, I missed it. 5 modulo 3 is 2, 7 modulo 3 is 1, so 2 into 1 is 2, alright. Now 5 into 7 modulo 3 is 35 modulo 3, which is 2, so it holds, right? So you can work it out, you can work out the proof, it's very straightforward. Alright, so this is something that modular arithmetic follows. You can break it down into individual components, multiply, like take modulo and then multiply it and take the modulo again. It has this property of like associating or like dividing it into the distributive property, I think. Got it? So that's what we're going to incorporate it in our code. Alright, long power of LL base, like we're calculating a to the power b modulo p. A to the power b modulo mod, like this is the number. LL long a, LL b. Alright. Now, one way is to just LL answer, we just iterate through a loop. Answer. Int I equals 1, I less than equal to b, I plus plus, answer equals answer into a, return answer. To calculate 2 to the power of 2 comma 10 to the power 5. This is going to give you an error. Why? We can just see it now. Answer. It's going to print you some garbage likely. Yep. See, it's not going to give you the right answer. Whereas if you do this, it's going to give you the right answer. Power of 2 comma 4, 16. It gave you the right answer. But if you do a big number like 2 to the power 10 power 5, it won't give you the right answer. Why? Because 2 to the power 10 power 5 is a huge number which does not fit into the long, because long is only up to 10 to the power 18. and that's why it prints some random. It prints another number which is like not correct. It prints 0 in this case. But internally, it prints 0 because internally, like the number rolls over after, since our long is 2 to the power 64. It prints, like internally you don't need to know this like to solve problems, but internally the computer just prints to modulo 2 to the power 64. For example, that's why 2 to the power 10 power 5 modulo 2 to the power 64. 2 to the power 10 power 5 is a multiple of 2 to the power 64. That's why it prints 0. But like this is just to, like, you'll just get confused about what the computer does. That's not required. All right. But however, 1E5. I hope everyone's following me. Modulo mod. Yep. This will give you the correct answer. So this is a huge number. It is not exactly 2 to the power 10 power 5, but it's 2 to the power 10 power 5 modulo this prime number, this big prime number. But you know what? This is really slow, as we discussed. Let's do the binary exponentiation method that we taught in class 1. Can someone comment in the chat what the complexity of binary exponentiation is? I'll just meanwhile I'll write the code here. A, if b modulo 2 equals if base case b equals 0, return 1, else LLX equals power of a comma b by 2 if b modulo 2 answer equals answer into answer. Awesome. Sumit overflog n, Rahul overflog n. That's correct. Oh no. Rahul says n log of log n. It's log of log. It's overflog n. I'll tell you why. Else, if you followed my if you don't know it yet, like if you're not convinced yet, I suggest you to watch my first video. It's exactly on this. All right. Remember the number. Previously, without this is using the brute force, we'll get the same number again. Wait one sec. What? X. See, we all make mistakes. It's okay. Perfectly fine. Yep, we got the same number. 2 to the power 10 power 5 modulo mod. All right. Easy. Okay, all right. So what did we do here? At every multiplication, you need to take a mod. You should not miss even a single multiplication where you don't take a mod. All right. Even if you take if you don't do this, you'll get a wrong answer. See, you'll get a different answer. Oh wait, here you got like say 3 to the power 10 power 5. One sec. It's only because one sec. Alright, basically you need to take a mod at every step. Alright? You need to take a mod at every step, otherwise you'll get a wrong answer. You'll likely get a wrong answer. Very likely. So you need to take a mod at every addition and multiplication. Alright? And whenever you think it's going to go negative, you add a mod. Alright? You just add a mod. Awesome. So this is how we compute a to the power b modulo p. Does anyone have any questions here? Like I'm here to answer that. I'm here to answer. Like if it's clear, can you please comment clear so I know it's like you've all understood it? Can you please comment clear, saying that you're clear? Okay, any doubts, please let me know. I'll answer each one of them for you. So, I'll just open the window. All right. Now, calculating factorials. What's a factorial? Factorials are like n factorial is given by the number of ways you can rearrange n items and distinct items, which is basically n factorial. Like 5 factorial is 1 into 2 into 3. All some like multiply all numbers from 1 to whatever n. That's n factorial. Satish asks, do you know Telugu? Yeah, I know Telugu. Yeah, I speak Telugu. Thanks, Sumit, Kansham, Mamta. First morning. Rahul asks, yes, Nitin, I know Hindi. Rahul asks, so will you teach DP? Yes, I will teach DP. But, like, you need to get your math straight. Like, math is your fundamental. Math is your, like, core fundamentals of, it's one of the core fundamentals of, like, getting good at CP. And that's why I'm stressing a lot on math. It's really helpful to, like, if you're good at math, it's usually easier to progress faster in CP rather than knowing a programming language. Like it's easier for a good math guy to do CP rather than a programming guy to do well at CP. That's just my observation, but yeah. Awesome. Rahul says 5 factorial is 120. Awesome. That's correct. All right. Let's see how we calculate factorials. Let's just do it via code. Like, I won't I'll explain it via code itself. Okay. Sumit, okay. Please also take a class on combinatorics and PNC needed for CP. All right. So my plan is, the next class I'll be taking modular arithmetic, and then I'll do a couple of problem solving sessions. After which I'll go to CP. I'll go to combinatorics and combinatorics and permutations and combinations. Is that okay? Or do you want? Would you like suggest a different pattern? I'll see if I can incorporate that. Now, how do you calculate factorials? No, you want to calculate n factorial. Factorial. LL, answer equals 1. Now for int I equals 1, I less than equal to n, I plus plus, answer into equals I, return I. Return answer. So now CR factorial of 5, as Rahul mentioned properly, we get 120. Great, awesome. But if we write 10, you'll get another number which is like huge, 36280. That's correct. That's also correct. But if we take 100, note that we are not taking mod yet here. We'll see the consequences of not taking mod. You'll get a garbage number, which is 0. 35. It's again a garbage number. We know that 35 factorial needs to end at 0, right? 35 factorial needs to end at 0 because 35 into 34 into 30, 35 into 34 ends at 0. Multiple of 5 into multiple of 2 ends at 0. And so that the number has to end at 0, but clearly it's not ending at 0, which means the number is faulty, which means there's an overflow happening. All right. This is the main reason Sumit, you mentioned there's a CF blog. I think it'll be useful for all of them if you link the CF blog as well. All right. So answering into equals I. What we do here is answer into I modulo mod. Now we'll get the correct answer. Like we'll get the correct modulo mod. All right. This is the main reason they are like, since factorials and powers, they can get really huge. All right. They can get really huge, and to wrap them around into a smaller number, a mod is introduced. All right. All right. And yes, anything after 5 factorial will end with 0. All right. Awesome. This is very simple, right? Now, any doubts so far? All right. Now, Fermat's theorem. You might have heard of what Fermat's theorem is. Let's discuss it. All right. Does anyone know what Fermat's theorem is? What's Fermat's theorem according to you? What's Fermat's theorem? Please tell me what Fermat's theorem is. All right. So Fermat's theorem states that for any prime number p, all numbers a from 1 to p minus 1, like take any number from 1 to p minus 1, raise it to the power p minus 1, like say a, take a number a from 1 to p minus 1, a to the power p minus 1, that number, a power p minus 1, that number gives a remainder 1 modulo p. All right. Yep. So, it's p power n. Someone says p power n. So Yash says I don't know. All right. That's what you don't know. Yeah. All right. No problem. I'm going to teach you that. Fermat's theorem states that okay. All right. A to the power p minus 1 is equal to, this is a reminder, modulo p equals 1. This is what it states. All right. All right. A to the power p minus 1 modulo p is 1 for all primes. All primes p and 1 less than or equal to a less than or equal to p. Got it? Now, fair. Now, how did we get this? Like this? Well, this doesn't come so easily, intuitively, right? Sandesh says, okay. All right, Sumit, nice one. And how did we get this? So, let's keep this as is. Now let's take like how did we get this? Like I'll tell you the proof later, but let's just take a few examples. Let's take p equals 5. All right. Now take any number a. Pick a number a. Now a to the power a say 3. 3 to the power p minus 1. What's 3 to the power p minus 1? 3 power 4. 3 to the power 4 is 3 square 9 power square. 9 square 81. All right. 81 gives a remainder 1 modulo 5. Satisfied. Let a be 1. 1 power 4 gives a remainder 1. Awesome. 4. Let a be 4. 4 to the power 4. 4 square is 16. 16 square is 256. 256 is 255 plus 1. It gives a remainder 1 modulo 5. Holds really well. So Yash asks if a is also prime. No, it's not necessary. A can be any number from 1 to p minus 1. In fact, it can be any number which is not a multiple of p, but for simplicity, I just stated that a more general condition is a modulo p not equal to 0. All right. This is not required. This is a strict, like it's a strict condition. It's not required. I just told that to like make it simple for you. But in general, A should not be a multiple of this prime, P. Let's take P equals 7, a bigger number. Let's see if it holds here. Now, P equals 7. Let's take A equals 5. Let's see what 5 power 6 is. 5 to the power. Let's just do it in our own method. Like we just wrote a. We just wrote a power function. Let's take 7. See out power of 6 comma mod minus 1. See, you'll get 1. Take the mod to be very big, as we discussed before. 110 to the power 9 plus 7. I can just write it as 1e9 plus 7. Alright. Now, 6 to the power mod minus 1. Note that mod is so big. Now, if it's going to hold here, that means Fermat's theorem has some strength to it. Like, it's holding for all primes. A to the power p minus 1 is 1 mod p. Let's see if it holds. I didn't run it yet. Shall I run it? Cool, I'll run it. See, let's see. Wait, one sec. I'll just clear the output and run it again. Yes, Sumit says, yeah, Fermat's theorem is also using, yep, as you can see, 6 to the power p minus 1 is p. Like, if you take any random number, 1 again. So, that's the magic of Fermat's theorem. It relates powering up any number, like, any number to the power p minus 1 gives you 1 basically, except the multiples of p including 0. Siyash says run the program. Yep, I just did. Yep. Like, but if I run say mod minus 2, it won't give me a number like that. Yeah. So it gives me some garbage here. It's not garbage exactly, it has something to it, but per mod minus 1, it gives me 1 directly. Alright. Pawan asks, which IDE do I use Sublime. Awesome. Now I'll tell you the proof. It's really beautiful. It has 3 proofs to it, but like I'll give you the simplest one and the one which is really intuitive, so that it gets imprinted into your head. Yeah, it is indeed magical. And Fermat's theorem, it's a subpart of number theory, and it's one of the beautiful topics of number theory. Like, not Fermat's theorem itself, but taking modular primes. It's really beautiful. Like, I'll just tell you. I'll just tell you why. All right. Now you know what Fermat's theorem is. We'll discuss its proof. We need, like, see, I'll tell you. Now, honestly speaking, Nikaru Hakamura, nice name. So right now, I'll just tell you how it's going to be used. Problems not today. There's a problem solving session which is going to happen, and I'll clear those concepts for you. All right. Yeah. Like, apply these concepts in real life, in not real life, and in different problems, math problems as well. All right. Now, a to the power, where was I? Yeah. I'll give you the proof, and you, honestly speaking, you don't need the proof, but you know what, like, knowing the proof will just build your mathematical understanding even more, and it's going to clear up, it's just going to strengthen your fundamentals. You don't need to know the proof. Like, you can go up to level, I think you can do really well without the proof as well, but you know, to stand out as a programmer or as a computer programmer, it's really good to know all the proofs. Like, at least give it a try to understand the proofs, you know. it'll go a long way. All right. So yeah, sure. Awesome. The proof. Let's take the numbers. So we have A, right? Let's take the numbers A, 2A, 3A, 4A, 5A, so on till P minus 1 into A. I'll just erase these parts. Right. I'll just make it shorter because it's too big. Take these numbers A modulo P, 2 into A modulo P, so until P minus 1 into A modulo P. Alright. You have P minus 1 numbers here. You have P minus 1 numbers here. A modulo P. Note that A is not a multiple of P. Just note this like it's given. A is in a multiple of P. Alright. Why am I losing this man? One sec. Yeah, A is in a multiple of P. And another thing is P is prime. One second, let me format this so it looks good to you. P is prime. Alright. A is a multiple of P and P is prime. What's this? Let's get it out. Yep. How much time will it take to reach 1800 plus in code forces? Honestly, it depends on how you manage your time and how efficiently you solve problems that are challenging to you. It's about learning new things. When you're solving every problem, you need to learn new things, and that's how you grow. And keep giving contests. Keep giving contests. I can't stress this enough. Keep giving contests and upsolve. That's very important. Upsolving is very important. That's where the learning happens. Real learning happens. Giving the contest, it is educational, but the real learning happens when you're upsolving and learning new concepts. And how much time will it take? Honestly, it can take 5 months. It can take a year. I think for me, it took more than a year. It's perfectly fine. Go at your own pace, and more importantly, enjoy. That'll take you a long way. If you don't enjoy like it, you'll just burn out quickly. And so don't stress yourself about, yo, my rating isn't going up. Am I doing it right? Is this for me? If you're enjoying it, you'll go a long way. If you're doing it for interview preparation, that's a different story. But if you're doing it for fun and so on, you need to enjoy it to go a long way. All right. Awesome. Now, these numbers, A modulo P. Oh, sure. My user ID is sinus_070. I can just write it down here. I'll just write it down here. You can see how I struggled in the start, and whenever my slope went up, it was usually when I started upsolving contests, and I just solved a lot of problems. I solved shit ton of problems, simply speaking. A lot of problems. Alright. Okay. Now look at these numbers. I'll explain the proof now. A modulo P, 2A modulo P, so until P minus 1 A modulo. Now, let's just make a bold claim saying that all these numbers will be a shuffle of 1, 2, I'll just all these numbers will be a shuffle of 1, 2, where's the text here? All these numbers will be a shuffle of 1, 2, 3, 4, so. Yep. Alright. My claim is that all these numbers, A modulo P, 2A modulo P, 3A modulo P, and so on till P minus 1 A modulo P, will be some rearrangement of 1 to P minus 1. That is, if you sort this array, you are going to get all numbers from 1 to P minus 1 exactly once. Alright. Now, you might question how. You might question how. Like, where does this come? Like, how do you know everything, or every number from 1 to p minus 1 occurs exactly once? How do you know? How do you know that something doesn't repeat? Let's just check if it actually occurs every time from 1 or 1 to p minus 1. Via code itself we check, okay. Since, like, it's hard to do from 1 to mod minus 1 where it's 10 power 9, let's take a bigger number. Let's take the number 101. I equals 1 I. Please let me know if you have any doubts. I am here to explain them. Now, int we know that the prime is 101, so we iterate int values. Okay, now values of, or we can directly declare the array, int values of mod. For int I equals 1, I less than equal to mod minus 1. What do we do here? Let's take any a. Int a equals 7, for example. All right. Mod minus 1, I plus plus. We all make typos, okay. Values of I equals power of a comma. Sorry. See, I'm not yet going to the proof. I'll tell you the proof and I'll tell you the magic later. But let's just look at this. A into I. This is another magic, okay? Another magic. Values of I equals a into I. A into I modulo mod. Remember, at every multiplication we need to take a mod. Now, alright. Let's first print values. I equals 1, I less than equal to mod I plus plus C out values of I. We're going to get a bunch of numbers in some random order. Oh wait, I forgot to print the space, sorry. You got a bunch of numbers, and if you notice closely, you might see that no number is repeating. I mean, it's hard to compare here, but I'll show you how no number is repeating. We saw this in print. Values. Now we see that all numbers are in increasing order. Yep. That's your magic. So you take I, 2i, 3i, 4i, so on till p minus 1 into I. You sort them. Turns out each value occurs exactly once. That's another useful conclusion from this. See, when you're actually learning the proof, you learn different ideas. And competitive programming is all about coming up with different ideas and discarding each one of them and moving to the next idea quickly. So when you're learning the proof, you just learn different ideas and conclusions. So this is why it's important to learn proofs. I mean, it's okay if you don't learn them, but it's beneficial if you do. Can everyone see what's happening here? I'm just claiming that if you sort these numbers, like a, 2a, 3a, and so on till p minus 1a modulo p, all of them are a different arrangement of 1 to p minus 1. Is that clear? Can everyone see that? Please let me know if it's clear, or if it's not clear, I'll explain it again. I really like some feedback. Yeah. Why a into I? I'll tell you. Original equation is this. I'll get there slowly. You might think, how is this related? How is what I'm doing here related to this? I'll get there. Okay. All right. Now, if we multiply so this is basically, yes, everyone has this really tricky question, why a into I not a power I or a power p minus 1. I'll get there. That's the magic part. I'll get there, slowly get there. Now we have these numbers, right? We have these numbers. Sumitawa, I just Sumitawa Chakraborty asks, you didn't get the sort part. The sort part was just to explain that how each number comes exactly once. Wow. And one more thing, note that all these numbers are different. All these numbers have to be different, because if two numbers are same, let's say all these numbers have to be different. I into a, 2 into I into 1 into a, 2 into a, 3 into a, so on till p minus 1 into a. I know you must be confused here, but just hold on for 5 minutes and I'll explain you everything, and everything will fall into place for you. All these numbers, 1 into a, 2 into a, 3 into a, so on till p minus 1 into a, all of them are going to be different, right? Why? Because a is not a multiple of p, and say two numbers are different. I into a modulo p equals j into a modulo p, meaning let's say where I into a modulo p and j into I into a and j into a give the same remainder modulo p, which means that the difference between I into a and j into a has to be a multiple of p, meaning ia minus ja modulo p equals 0, which means that a into I into j modulo p is 0, right? This is what implies. This is what implies. It says that a into I minus j gives a remainder 0 modulo p. But we know that a is not a multiple of p, we already discussed. And I minus j cannot be a multiple of p, because I and j are from 1 to p minus 1. That's the proof, okay? That's the proof for all of them being different. Now, let's see how this relates to a to the power p minus 1 modulo p equals 1. Now, here's where the magic comes. So now, you multiply all these numbers, okay? You multiply a into 2a into 3a into 4a into so on, p minus 1 into a. We take this modulo p. Alright. Multiply all these numbers. Alright. And we get, what is this equal to? Equals p minus 1 factorial into a to the power p minus 1. Correct. Alright, this is equal to this, right? Like a comes p minus 1 times, and if you take a out, you get 1 into 2 into 3 into 4 into so on till p minus 1. Alright. Now, we know that a, 2a, 3a, 4a and so on till p minus 1 into a, all of them are a rearrangement of this. We also know this. You know that this, I'll just clear some things here. It's time to clear. One sec, I'll just put this up. One sec, why am I messing this up? I'll just clear this. Yeah. Alright, now you multiply all of them. A into 2, A into 3, A into 4, A so on till p minus 1 into A. You get p minus 1 factorial. Alright, and then we get a into a p minus 1 times a to the power p minus 1 modulo p. Alright, this is one way to look at it. What's another way to look at it? Another way to look at it is, this is equal to, we know that if we rearrange this, we're going to get 1 to p minus 1, right? So you're going to get 1 into 2 into, like in some order, like maybe in some order, but you get, if you multiply all of them, you'll get it's a rearrangement of this. So 3 into, you might be getting 4 into 3 into 2 into 1 into p minus 1 into p minus 3 into so on, but some arrangement, but it will be multiplication of that, like 3 into 4 is same as 4 into 3. So we know that each of these numbers occurs exactly once. That means if you multiply all of them, you should get 1 into 2 into 3 into so on till 4 into so on till p minus 1 modulo p, which is again p minus 1 factorial if you modulo p. Note that so we did it using this way, like we just multiplied the individual terms a into 2 into 3a. That will give you, if you take the a separately and 1 to p minus 1 separately, it's going to be 1 into 2 into 3 so on to p minus 1. Note that since this is one way and this way is using this observation that we multiplied, that each number modulo p occurs exactly once. Alright. Now this number has to be equal to this number, meaning I'll just clear the whole thing for now, meaning one second. One sec. Yeah. This number इधर जो है, this number and this number have to be equal, right? Look here. Meaning p minus 1 into a power p minus 1 modulo p, this number and this number have to be equal, which means a to the power p minus 1 has to be equal to 1 mod p. That's the only solution. Like, what did you get here? This part equals I'll just tell you. 1 second, folks. We got this. Note this. Look at this. Both of them should be equal to 0. Both of them should be equal to 1. So p minus 1 factorial modulo p is equal to p minus 1 factorial into a power p minus 1. Matlab, this gets cancelled out here and here, meaning we are remaining with this being equal to 1. Very simple. Alright? That means ये cancel हो गया. We can cancel this, and then we remain with this being equal to 1. Fair, straightforward. I mean, it's a bit hard, I understand, but you know. And Nikaro is asking a into 2a into 3a so on to p minus 1 modulo p is equal to 1 into 2 into 3 so on to p minus 1 modulo p. Is it just intuition or is it's a theorem? Well, it's not intuition. It has a solid proof for it. Yes. So the proof is like what do you say? That a 2a 3a modulo p so on till p minus 1 into a modulo p. The proof that all of them occur exactly once, all of them are different, and all of them are from 1 to p minus 1. The proof is, say two numbers i into a and j into a give the same remainder modulo p. Just say like it's not happening. So to prove it, let's prove a contradiction. Let's say they give the same remainder modulo p. Let's say I into a and j into a, where I and j are from 1 to p minus 1. That's what I into a and j into a. Let's say both of them give the same remainder modulo p, which means if you subtract, the difference should be a multiple of p, right? If two numbers give the same remainder modulo p, the difference should be a multiple of p, right? Now, I into a minus j into a should be a multiple of p. If you take a common, a into I into j should be a multiple of p. We know that a isn't a multiple of p. We've established that, which means I into j has to be I minus j has to be a multiple of p. But we know that I and j, both of them are from 1 to p minus 1, which means I minus j cannot be a multiple of p, right? Because I and j both are from 1 to p minus 1 and p is a prime. I minus j cannot be a multiple of p in that case. That's the reason That's the reason this will be equal to this. And we showed that via code as well. We took the prime as 101, 101 as a prime. It doesn't have any prime factors, like other than 101 itself. And we checked we took a number a, 7, which is from 1 to p minus 1. We took all its multiples, 7 into 1, 7 into 3. And then we sorted all of them, and we saw that each one is occurring exactly once. 1 to p minus 1 is occurring exactly once. Now, what we did is, we multiplied them. Multiplying them, we can just rearrange and say, since each number from 1 to p minus 1 is occurring exactly once, we say that, since each number is occurring exactly once, we can say that, we can multiply them, we can just write it as 1 to p minus 1 multiplied with each other. And we are comparing it with another way of computing it, which is a, 2a, 3a, and so on. We take a common, a is occurring p minus 1 times, and we take the coefficient again, common, p minus 1 factorial into a to the power p minus 1. Now, since these both values are same, like just that we are computing them in different ways, I mean, we are computing them correctly. It's not like we are computing them in a wrong way. Since we are computing them correctly, they have to be equal. Like same formula, दो तरीके से compare कर रहे हैं, दो तरीके से compute कर रहे हैं. Like we compute in two different ways, so they have got to be equal. All right. Now we compare p minus 1 factorial into 8 power p minus 1. So we just wrote that here. One second. This one we wrote it here. We wrote this here. This is another way of computing. We wrote this here. Now both of them have to be equal. No, both of them have to be equal. Like we computed them correctly. Though, like we computed them correctly. Now they have to be equal. Now we solve the equation. Like p minus 1 factorial is common in both of them. We can remove them. Now this value has to be equal to 1 because the a power p minus 1 modulo p equals 1 modulo p. Very simple. So Hikaru says, is there a name for these kind of proofs? I mean, you can call it proof by contradiction, but you can call it a proof. Bunny says, super duper interesting. Thanks. Yeah. Is this clear? Is this all clear? You might think this proof is going to be useless. Like, why do we need proofs? But note that that's where your understandings build up. Like, someone asked a into a, 2a, 3a, 4a, surrounded p minus 1a. Is it intuition or is it a theorem? Well, if you don't learn the proofs, if you treat it as a black box, it's the theorem. But if you learn the proofs, it's going to come intuitively to you. That's the difference between knowing the proofs and not knowing the proofs. And knowing things intuitively can be useful in solving harder problems. Alright? So, if you have any doubts so far, please let me know. And if it's clear, please let me know that too. But if you have any doubt in this proof, like any simple doubt, like I'm here to explain it to you. I'm checking the live chat if you have any doubts. Any doubts? See, one thing is to, like, you can learn a power p minus 1 is 1 mod p, and you can solve up to a certain level, and you can, right? If you have any doubts, I'm here to explain. Please ask them to me. I'm yours to explain. Yeah. Okay. Divakaran has a problem, so let's explain it to him first. No problem. Can you repeat that a into 2a part? Okay. So, one sec. Let me. I'll explain that a into 2a part once more. Yeah. All right. Now, what did we see here? A, 2A, 3A, 4A. Like, I'd like to explain it clearly, so I want everyone to understand it. It's okay to not understand at your first go. So until P minus 1 into A. Now, what did we say here? I'll just revise the proof again. All these numbers, modulo P, like you take these numbers modulo P. If you take these numbers modulo P, and now if you rearrange them, let me get this bigger. Yeah. Now if you rearrange, it's like basically sort. You get 1, 2, 3, so on to P minus 1. That's the magic here. Know that I'm taking modulo P here. So every number comes here, every number from 1 to P minus, every number is going to be from 1 to P minus 1. And the claim is that each of those numbers occur exactly once. Alright? That's the claim. And the proof was proof by contradiction. It's a very common proof. Proof by contradiction. Say two numbers are equal. I into A equals I into A modulo P equals J into A modulo P. What does this mean? This simply means that I into A minus J into A is a multiple of P. Now if I into A into J into A is a multiple of P, it means that you can take I into A common. I minus J into A is a multiple of P. We know that A isn't a multiple of P. That means I minus J is a multiple of P. But I and J, both numbers are from 1 to P minus 1, which means I has to be equal to J, but we came to the conclusion that I cannot be equal to J. We took two different numbers, right? So we arrived at a contradiction. That's how all these numbers are from 1 to P minus 1. I'm missing something here. Yeah. So all these numbers are from 1 to P minus 1 and no two are equal, and there are P minus 1 numbers. So each of these numbers falls into one of the 1 to P minus 1 buckets, exactly one of them. So 1 to P minus 1 occurs exactly once. Now what we did was, we multiplied A, 2A, 3A, 4A, so on till 5A, so on till P minus 1 into A. And we computed it using two different methods, both of which are correct. That's important, both should be correct. First method is we blindly multiplied them, no observations, nothing. A into 2A into 3A, we took A common in each term, A to the power P minus 1 into 1, 2, 3, 4, 5, so on till P minus 1. We get A to the power P minus 1 into P minus 1 factorial. Alright. We took another way using our observation that each number from 1 to P minus 1 occurs exactly once. We came to the conclusion that A into 2 into 3 so on till P minus 1A is also equal to 1 into 2 into 3 into 4 so on till P minus 1, because 1 to P minus 1 each number occurs exactly once. Correct? It occurs exactly once. Meaning, you can just multiply them, just that the order is different. Who cares about the order when you're multiplying, right? So now what we did was, we just equated those two correct ways to compute. Okay, we just equated those two correct ways to compute. Now once you equate like two correct ways to compute, the answer has to be same. You computed them the correct way. Meaning, P minus 1 factorial modulo P is equal to P minus 1 factorial into A power P minus 1. Meaning A power P minus 1 has to be equal to 1. A power P minus 1 has to be giving the remainder of 1 modulo P. Straightforward. So now has everyone understood? Like if it's clear, please let me know. Or if it's not clear, please let me know that too. Alright? Here to explain. And I'll tell you how this is useful in problems. Everything's clear? Awesome. All right. The credence clear. Awesome. All right. Let's clear this now. We got now. You must have heard of Fermat's theorem multiple times. Nitin is asking, why will it not work if A is a multiple of P? If A is a multiple of P, then A to the power P would just be 0, right? A is a multiple of P. A will only give you, that means A modulo P is 0. It won't be equal to 1. That's the only reason. Is that clear? Yep. Awesome. Now, I was thinking of something. What is that? Yeah. A to the power P minus 1 is 1 mod P. Awesome. What did we hear? Like, what did we get to now? Superscript. Is that superscript option? No. All right. A to the power. No, it's okay. It's good to ask questions. A to the power P minus 1 is equal to 1 mod P. All right. Now, we can write this as A to the power 0 as well, right? Huh? Correct. You can write this as A power 0. Now, turns out, like, let's discuss what an inverse means. There is something called A to the power minus 1. Minus 1. Love. 1 by A mod P. Like, it can be as simple as, like in some questions they can ask, in some problems they can ask you to print an integer, like print the probability as an integer. Like, or you might ask, like, probability as an integer. I mean, probability is supposed to be from 0 to 1. Most, like almost all of the times, probability is going to be a real number. But no. So probability, say they can say the answer you get the answer as 7 by 12. And they ask you to print it modulo something. Now we just notice that modulo is defined for integers. Now it's a fraction. What am I going to do? Well, first let's try to represent 1 by A as an integer. So let's what does 1 by A mean? If x equals 1 by A, what does it mean? Like in general, what is, like, if some number is equal to 1 by A, what does it mean? 0.5. It's a number which when divided by, like, 1 by A is a number which when divided by A gives 1. I mean, this seems dumb, right? Like, I mean, yeah, that's obvious. But it's not so obvious in terms of taking modulo. X is a number where x into A mod P equals 1. Alright. Now, this might seem a bit confusing. That's okay. It is confusing. It's meant to be confusing. Okay. That's how it is. Now, I'll just bring this up down. So, we know that A to the power 0 equals A to the power P minus 1. From now on, like when I'm using modulos, I won't write modulo P every time. Just note that. I won't write modulo P every time. Now, it's assumed that I'm taking modulo P every time, okay? Like when I'm writing A power P minus 1, it's assumed that I'm taking modulo P. Alright? This is just to simplify how you look at it, like simplify explaining it to you. Every time from now, I'll skip this. I'll skip mod P from now. Alright? Is that okay? Let me know if you have any problem with that. Now, A power 0 equals A power P minus 1. Now, what is 1 by A? Can anyone tell me? A to the power minus 1 equals what? I want you to answer this. What is a power minus 1? Tell me. If a power 0 is a power p minus 1, a power minus 1 is, I mean, one way to write it is a power 1 minus p. 1 minus p, like, sorry, actually, you tell me. That's the wrong way. Like, tell me, what's a power minus 1? I want you to think and tell me. One by a, that's correct, but I want you to tell me in terms of a to the power x. Inverse. Okay, I'll explain it to you. It's essentially a to the power p minus 1 into, this is basically, you can write this as a to the power 0 into a to the power minus 1, right? Alright. Now what is a to the power 0? This is just a power p minus 1. A power 0 is a power p minus 1. So, a to the power p minus 1 into a to the power minus 1 equals a to the power p minus 2. That's it. A power minus 1 is a to the power p minus 2. It's as simple as that. Alright. So, we know that we cannot compute this a power minus 1. We can't do this using binary exponentiation, right? We can't write a to the power minus 1. We can write only where b is greater than or equal to 0. So we just write this as a power minus 1 can be written as a power p minus 2. Why? We discussed that the inverse should be such that if you multiply it by itself, it should give you 1. Like a to the power minus 1 into a. Let's see what a, we can write a 1 by a equals a to the power p minus 2. Alright. Now, this holds the property that, I'll just push it down, a to the power p minus 2. If you multiply this by a, you get 1. Why? Because a power p minus 2 into a is a power p minus 1, and by Fermat's theorem, a power p minus 1 is 1. So, for all practical purposes, 1 by a, you can write it as a to the power p minus 2. Note that everything is modular p. Alright? All these numbers are from 1 to p minus 1. Just note that. And a is in a multiple of p. If a is a multiple of p, then it's nothing, none of it is defined. This is only for a from 1 to p minus 1. Is this understood? So this is our crux. So by, like, essentially you're getting 1 by a into a equals 1. Is this understood? Let me know if it's clear. So every time when you are asked to print 1 by a fraction in terms of fraction modulo p, say you want to print 1 by 5 modulo p, you just take 5 power minus 1 and you write that as 5 power p minus 2, because 5 power p minus 2 is same as 1 by 5, right? 5 power p minus 2 and you print the answer simply directly, and that's it. If you're asked to print 1 by 5 power p minus 2, that's it. If you want to see this in action, I'll show it to you via code. Let's take, we have P101. Let's take a as a equals 23 int inverse of a to the power a comma p minus 2. Now we'll see that a into, let's print in a first, What's going on? Oh, mod 22. Alright, we got inverse of s 22, which means 23 power 2, 101, 23 power p minus 2 is 22. Alright, now we'll see that 22 into 23 modulo 101 gives you 1. Satisfied, right? You multiply it by itself, you multiply inverse of x by into x, you get 1, and that is satisfied. We just saw that in action. Do let me know if you have any questions, and if it's hard to understand, I can explain it to you again. Is this clear? All clear? I'd like you to respond, because that's how I know if I've taught it correctly or not. Awesome. Nothing. What do? We just try to represent a fraction. And the first step to representing a fraction is representing 1 by x. Now, answer. Thanks, Rahul. Now, say you want to calculate a by b modulo p. Now, I want you to tell me how would I do this? How do you do this? How do you do this? Like a into a. Now, if I want, we just calculate how to calculate 1 by b modulo p, like 1 by a modulo p, something. Same thing. We know how to calculate 1 by b. We know how to. Safra, understood. Thanks, Devakaran. Now, how do you calculate 1 by b? We know how to calculate 1 by b. Yes, Safra has the answer. How do you calculate a by b? It's essentially, let me make this big. We can write a by b equals a into b inverse. Correct. Now, this is basically a into b to the power p minus 2. Alright, we are done. That's it. A into b, this is a by b equals a into b power p minus 2. Awesome. We can just verify that if you want. Okay. Reiterating it, a by b, we can multiply that as a into 1 by b. 1 by b is essentially b power minus 1, inverse of b. And inverse of b, as we discussed here, inverse of b is just a to the power p minus 2. Alright. So b, a into 1 by b. So if you want, int compute int a, int b. So we are returning a by b modulo mod or p, whatever you want to call it. Return power of a into power of b comma minus 1, but it doesn't accept minus 1. That's why we are writing p minus 2 modulo. Yeah, this is very straightforward. Okay, we just discussed everything. We know each and every bit of our code. Like we know each and everything what our code does. We know how power works. We know why we are doing this. We know why inverse is being taken and how the proof of inverse came, right? Like we know before that how it came from Fermat's theorem, because, and how Fermat's theorem came, we know that as well. Like we know each and every proof of what's going on here. All right. we know each and every small bit of what's going on here. What else do you need? Now, say we want to compute 3 by 7. 3 by 7. And I'm executing code right in front of you and it's working. Compute 3 comma 7. If I compute, you get, wait, I got a compilation error as usual. Compute, what did I miss? A comma 1. I mean, I just need, that is stupid. A into B, A power 1 into B power minus 1, this is. Alright. Now, and that's another compilation error, not minus. Alright. I got the number 87. A by B is number 87. Now let's verify. No, thanks, Rahul. I missed that. So let's verify. I got 3 by 7 equals 87. Now what's one way to verify? Let's say 87. 87. 3 by 7 equals 87, right? Alright. Let's verify this. Let's multiply by 87 by 7 and we need to get 3. 87 into 7 modulo 101. Yep, you can see that we got 3. Perfect. Like we just verified it and it works. We saw that in action. And I want you to try it out. I want you to play around with this program a bit. And I want you to write it down on your own. Don't copy code. Write it down on your own. Awesome. That's the beauty of this part actually. All right. Any questions? Do you have any questions so far? I really love to answer them. Any questions so far? So this is the numerator, this is the denominator. It's very straightforward. Any questions? Please let me know if it's clear. If it's not clear, I'll explain it to you again. Any bit which is not clear, I'll explain it to you. That's what I'm here for. Is everything clear? Awesome. All right. Safraj is asking, give some good problems. For now, give me a minute. Good problems. I really want to. Let me think. Honestly speaking, I didn't prepare problems for this class. I was thinking of doing it in a problem solving session. So I'll give it to you. Like, it's going to be a lot for you to take it in one class. So I'd suggest you to revise this once. Rahul is asking when will be the next session. I want to take a session on graphs and DP. Yes, that is coming soon. As I said, I want to focus on math first. That's my strong area, and I want that to be a strong area too. And Anuj is asking, short me. I will get to graphs and DP soon, very soon. Let's get good at math first. Math is the base for computer programming. Now, एक बार पूरा फिर से. ठीक है. I'll just tell it to you via words. First, we discuss what Fermat's theorem is. Fermat's theorem is you take any prime and you take any number a which is not a multiple of p. You raise it to the power p minus 1. Alright, you raise it to the power p minus 1. Let me see if I can find the concept history. All right, let's start from here. So what did we do? This is the format theorem. We take it to the power p minus 1. A to power p minus 1 is 1 mod p. And after that, how do we prove this? We then discovered that a into p, not discovered, like it's already discovered by many people, but a into p, a to a, 3a, so on till p minus 1 into a, all of them constitute 1 to p minus 1, right? All of them, if you rearrange them, no two of these numbers will be equal. We discussed why. Because if any two of them are equal, by equal I mean they give the same remainder modulo p, it means that the difference is a multiple of p, right? Now if the difference is a multiple of p, it means that either a is a multiple of p, or let's say those two numbers are I into a and j into a. Now the difference is going to be a multiplied by I minus j, and if they give the same remainder modulo p, it means that either a is a multiple of p or I minus j is a multiple of p. You know that a isn't a multiple of p, and I and j, both the numbers are from 1 to p minus 1, so I minus j can't be a multiple of p either. Got it? So that's how you get all these numbers are different. Now we found out a different way to multiply them. Where is that man? I guess I lost that. Fine, never mind. Now we multiplied them. So one way to multiply would be 1 into 2 into so on till p. If you multiply this, you get a power p minus 1 multiplied by p minus 1 factorial in one way. And in another way, you just get p minus 1 factorial. And now you can cancel p minus 1 factorial and p minus 1 factorial. So you get a power p minus 1 equals 1 mod p. And to take the inverse, since a power p minus 1 is 1, a power p minus 2 is going to be 1 by a. Very straightforward. Alright. And that's how we calculate fractions. Equals a into b to the power p minus 2 mod p. Alright. Straightforward. And that's it. Awesome. And we also, like, if you remember correctly, we printed all multiples of some p. So we took a equals 7 and we multiplied all multiples 7, 14, 21, modulo p, and then we sorted it. And then we got all numbers from 1 to 100, 1 to p minus 1, that is. Alright. Awesome. Any doubts so far? Any doubts? Any doubts? I'm here to explain them to you. Also, I hope everything's going well in your life. Like, I hope things are going good. And how's practice going? Sumit, how's practice going? I want you to comment it, chat, like, are you facing any problems, or what's your biggest concern when you're practicing? Anuj, Sarfraj, do you have any concerns like while practicing? Are you running into any problems, or is there anything bothering you? Rahul, yes, I'm at Google Dublin, yeah. I'm working there currently. Let me know if anything's bothering you. Yeah, all good. Let me know if you have any problems. I'm here to help you out with respect to competitive programming. Are you facing any problems while preparation? Okay. So with problems solving, what's the problem that you're facing? So you're not able to solve the first two of CF. So all right. First, let's address Sumit's question. You stuck at pupil for 7 months now. Okay. My pupil is all right. Let's go one by one. Sumit, not able to do DSA and CP simultaneously. All right. So I'd request you to focus more on CP because initially when you're a pupil, it's mostly about solving A and B consistently, A and B problems consistently. All right. One sec. Let me check one thing. All right. All right. Pupil, you need to do A and B consistently. So if you want to grow quickly, you need to solve more problems per day, and those problems need to challenge you. They shouldn't just be easy. And if you aren't spending 1 or 2 hours per day, I mean, time is not a good measure, but you need to be able to solve problems that are challenging to you, and it's okay if you don't get them. It's perfectly okay when you're practicing and you don't get them. It's about when you're upsolving, you need to spend like 15 to 20 minutes at least on the problem. You need to write down things. You just need to increase. You need to like try out more ideas. You need to be more brave. And even if you don't get them, that's okay. That's perfectly fine not to get them. And once you don't get them, you need to look at the editorial, and you shouldn't just like look at the problem and blindly implement it. You need to understand what the problem asks. You need to understand, hey, if this problem would have come, how should I have thought to arrive at the solution? And consistently doing this will help you get good. And you need to spend time. It's not going to come for free. I spent a lot of time. Like sometimes I spend 2 hours a day, 3 hours a day. I did it with a lot of dedication. Okay. Don't worry. Like if you're stuck at pupil, most importantly, you need to keep enjoying it, and that's how you'll get good. And not able to do DSA and CP simultaneously. Okay, that's okay. Like DSA and CP are highly correlated. You do CP, you do DSA. Like I guess CP is more like DSA. Like you can focus more on CP initially, and right before your interviews or something, you just focus on DSA. I think they're almost same, data structures and algorithms. Yeah. Sarfraj, you're not able to solve the first 2 of CF. Okay. Then the solution is simply practice. So if you haven't done like div 2b problems are usually just they don't require high level math or anything, very basic math. So I'd request you to go to past contests and solve B problems solve B problems consistently. If you solve around 30 to 40 B problems, I don't see a reason why you won't be able to solve the next B problem. So you need to keep practicing. Hold on, like you'll get there. It's gonna be it's hard before it gets easy. That's all I'll say. Rahul, take a session on upsolving code chef, code forces, and lead code. This is the plan for that too. So I plan to like do some code forces upsolving like B ladder or C ladder. So my idea is giving those problems to you beforehand and then solving them live. All right. Yeah. You can do the brute force, but then it becomes difficult. It's a good sign that you're able to code brute force. It's a good sign. But coming up with efficient solutions will only take practice. Like you just need to practice a lot. All right. Like there's no shortcut. Like I would be lying if I say that if you do these problems or if you do one way, you're gonna get to 1800 in a single day. I won't tell that to you because simply that's wrong. You need to practice a lot. That's all. Sumit, yeah, I apologize for like the big delay. I was moving to a different place and I simply didn't have time. I'm sorry about that, but I'll get more frequently. All right then. See you all in the next session. It's gonna happen next week. And have a great day. And if you have any doubts, please post it in the comments. I take a look at the comments before going to the next session. All right. Thank you. Have a good day.